Hello and welcome back to our control system lecture video. In our video we discussed the control system where we have no disturbance. So we talk about the open loop and we talk about the closed loop. Those are the major systems that can be categorized under control system. And with the closed loop we look at the positive feedback control system and we talk about the negative feedback control system. And the transfer function for the positive feedback can be, let's say, Tp equals to G on 1 minus G of H, and for the negative feedback we can say the transfer function can be Tn, which is equals to G on 1 plus G of H. And in this video we will look at the effect of the feedback control system, especially with the term sensitivity. So the effect based on the transfer function, how can it affect the overall transfer function for the positive and the negative, and how can the system achieve stability. To achieve stability we can now be looking at the effect based on the type of closed loop control system. And to recap our video, we can simply say that we have the system which is R of S, which is the input to the system, and we have a comparator, and we have the G of S, which is the gain of a controller plus the actuator in the S domain, and we have the output as the C of S, and we have H of S, which represent the feedback of the closed loop control system. And if this is a positive feedback control system, therefore we should have the input is added with the feedback. When we have both positive to the summation block, or we call it the comparator, because of this action it is now called a positive feedback. And for the negative feedback we mostly have the feedback which is intent negative. So for the positive we have Tp, which is the transfer function, or in most cases we can call the overall gain of the system, and this represents our system. And this system can be able to perform tasks based on the input and the output. So we have the G of S over 1 minus G of S, and we have H of S. So this is in terms of the S domain, or the frequency domain representation of the control system. And if you can remember, you have the G of S, which is the combination of the controller gain and the actuator gain. And we know that a controller can be a PI controller, PD controller, PID, the amplifier, a microcontroller. All of this can be regarded as a controller. And actuator can be devices such as a pump, a motor, a PWM, light, and so forth. And we can describe the G of S is equivalent to, let's say, G1 of S dot G2 of S, where G1 of S represent the controller gain and G2 of S will represent the actuator or the plant gain. And in that case this G of S can be having G1 of S and G2 of S. and it is now connected to C of S and to the comparator, and we have R of S as an input, and we have the H of S as the feedback. So this will be our overall control system diagram with representation of the controller gain, the actuator gain, feedback gain, the output, and the input. And for the negative feedback control system, we only have this one changed to plus, because we will have minus at the output of the feedback system, which is connected to the comparator, and it will minus the input signal, because it will now have the error signal E of S will be equals to the R of S minus the H of S. And this is very important when we talk about introduction of the noise, where we will now have a disturbance to the system, and we will see how the controller will adjust itself so that it can eliminate the noise that is occurring in the system. And firstly, we will now look at the effect of the feedback system and why it matters. In most control systems, the error signal, as we have discussed earlier, must be equals to the desired or the reference input minus the feedback, which is the H of S. And this is an important equation that we will discuss. And we all know that the transfer function of the negative feedback is equals to G of S over 1 plus G of S H of S. So we now have this as a numerator, and this is our denominator. And the important thing to understand with respect to the feedback is that if we consider this equation of a negative feedback closed loop control system, we know that the overall gain can be increased or decreased based on the increase in the value of the denominator and the increase or decrease in the value of the denominator. So our transfer function is known as the overall gain of the control system. Now, if our denominator 1 plus G of S H of S, if it is equals to 1, now we can have the overall transfer function is equals to G of S over 1, which is equals to G of S. And also the G of S is known as the open loop or the feed forward gain of the control system. And it can also be written as C of S over the R of S is equals to T on N over G of S, in order to know that the C of S is the response of the system and R of S is the input to the system. To find the response of the system, we now have C of S is equals to the G of S and the R of S. Now this is our feed forward gain times the input will gives us the output. Therefore, we know that this occurs when the denominator is equivalent to 1. Therefore, the response of the system will behave such that when we increase the input, which is the R of S, the output will also increase. If we decrease the input, we know that the output will decrease. And the gain of the system is basically a constant value when there are no varying parameters in the system component. However, in most systems, there are always noise that is added into the system, which will mostly affect the response of the system. And when we see that the denominator is equivalent to 1, in this case, we know that the system of the transfer function is proportional to the open loop gain of the system. Now what will happen if we say that the denominator 1 plus g of s h of s is less than 1? We can see that the transfer function Tn is equals to g of s with a value that is less than 1. When we keep on increasing the denominator which is less than 1, we can now see that this portion of the transfer function will increase. When we decrease this value, we know that the transfer function will increase. When we continue to decrease to a smaller and smaller value, the value of the transfer function will increase. And this represents the overall increase in the overall gain of the control system. Because with the analysis, we say that the overall gain, which is T of n, must be equals to C of s, and we have the R of s. And the output can be any value that is corresponding to the input, which is our desired value. For example, if we have 5 volts as an input, which we want to control the output, which is, for example, a speed, and these 5 volts must be correspond to, let's say, 2000 rpm as the speed. And in that case, to achieve 2000 rpm, we should have a constant transfer function multiplied by the R of s. And in that case, we can have the C of s, which is the response. And if we have an increase in the transfer function, that means the value of the denominator is less than 1. Now we will have this portion increase, and with a constant 5 volts, we may have value which is accumulating to the speed which is over 2000 rpm. And you can do math to confirm this identity. Therefore, to achieve this, we can have 2000 rpm divided by 5 volts. Now we should be able to get the value of the transfer function, and we can say the overall transfer function can be equivalent to 400. Since 400 will be a constant term, we say 5 volts is corresponding to 2000 rpm, and this T of s is equals to the feed-forward gain, which is the G of s. And when we say if the denominator is equals to 1, previously we say T of n is equals to the G of s. And in this case, the G of s will now represent the 400. And if we want to show it using the block diagram, can be like this that is shown here, where the T of n is equals to G of s, which is the feed-forward gain. Therefore, there are not much disturbance in the output. Therefore, we normally have the gain in the denominator 1 plus the gain of the feed-forward, and the feedback both will be equals to 1. And in that case, we can achieve stability. However, as we have made mention, if it is less than 1, therefore, how comes the value will be less than 1? Because we have 1 plus this value here. So if we want to have a value which is less than the value 1, it cannot be 0 because it will be unknown. Therefore, we know that the H of s is always negative in a negative feedback control system. And in that case, if the feedback is having a value which is greater, and if the value is greater with the feedback, we know that there is a disturbance with the output. Therefore, this value will be in a negative direction. Therefore, 1 will minus any value for the controller and the actuator, which is G of s multiplied by the feedback. We now should have a value here which is negative. So 1 minus a negative value will gives us a value which is less than 1. And the analysis such that if we have 1 plus g of s is equivalent to 400 and we have the feedback which measure the output such that 0.001, we now should have 1 minus 0.4 which can gives us 0.6, and this 0.6 is less than 1. We can look at the error. E is equivalent to R of S minus the H of S, and in that case we can have, for example, 5 volts minus 0.001, and now we can have 5 volts plus 0.001 volts, which is our error signal. And with the positive and negative feedback, in most cases error will be equals to 5 volts plus or minus 0.001 volts. And with the plus or minus, it can be a positive for a negative feedback like we have it here, or it will be minus in terms of a positive feedback system. And this is our error, and this can be represented as a percentage error. If it has to be a percentage error, we can have 1 to we have 0.1%, which is the error that is occurring in the system. Now we can see that this 0.001 is the feedback from the output, which can now tell us that the system with the denominator will be less than 1. In that case, we will have an increase in the transfer function of the overall gain of the system. And in the other case, we can have the transfer function which can be equals to g of s, where the denominator is greater than 1. When we look at the denominator that is greater than 1, that means a value of g of s and the h of s both must have a value which is a bit greater than 1. In that case, if we have a positive value of the h of s, which is the output of the feedback, we now can have 400 times 0.001. So this will becomes positive, so we can have 1.04. And now we know that 1.04 is greater than 1. And if you look closely with the error, we can be able to see that it will mostly have 0.1% error, and this will becomes negative. So in that case, R of S minus H of S, we will have 5 volts minus 0.001. And by then we can appreciate that if the gain of the denominator such that 1 plus g of s h of s, if it is greater or if it is less than, it is now corresponding to the overall calculation of the error, which can be plus or minus. And in most cases, we want that the transfer function must be equals to a constant value which is corresponding to the input and the output, such that the 5 volts is equivalent to 2000 RPM. And when we have a slight increase in the denominator of the transfer function, we will see an increase in the output or a decrease in the output, which may not correspond to a desired value of the input of the 5 volts. And in this case, we require a controller that can adjust so that we maintain a 5 volts which can produce 2000 RPM at the output. That is why we require a feedback, and the feedback such as the denominator of the overall transfer function becomes more important when we want to determine the overall transfer function T of n. Now we can provide a summary based on the effect of the feedback transfer function of a control system, such that if the denominator 1 plus g of s h of s, if it is less than 1, we have the transfer function T of n will increases. And when we have 1 plus g of s, h of s is greater than 1, we can now see that the overall transfer function will decreases. So these are the effect of the feedback of a closed loop control system. And this type of effect is very important to achieve the stability of the closed loop control system. And the key idea is to look at the denominator of the transfer function. And since we look at the g of s and the h of s, they are in the S domain representation, and the S domain representation are in the frequency range. Therefore, when we increase and decrease the value, we can see that the feedback will increase the overall gain of the system in one frequency range or decrease in another frequency range. They all now represent the effect of the feedback of a closed loop control system. Now we can look at the sensitivity of the overall gain. A overall gain of a system, when we talk about in terms of a sensitivity, how the system, especially the transfer function of the closed loop system, and the g of s, which is the gain of the open loop system, will vary, which will cause the transfer function to vary in such a way that it will affect the response of the system. And we can say that the sensitivity is equivalent to S T on G is equals to change in T divided by the change in G over G. And in this case, we have the percentage change in the overall transfer function T of n over the percentage change in G. And percentage change in the overall transfer function of a negative feedback system, and the percentage change in the overall gain of the open loop. Now this will give us a sensitivity computation of the overall system, how the system is sensitive in terms of its change in the transfer function and the open loop gain. And we can see that the differential change is the incremental change. So when we want to take this incremental change, we mostly use d on dt as a partial differentiation. And in that case, when we do partial differentiation with respect to g, or we can rewrite the equation such that s t on g is equals to d on dt and d of g dot g on t. And when we apply the partial differential, we can now have dt on dg is equals to d on dg. We now have g on 1 plus g of h. So we can have 1 plus g of h dot 1 minus g of h over 1 plus g of h squared. So it is now equivalent to 1 plus g of h squared. Now with this equation, we should get g on t, which is equals to 1 plus g of h. So when we substitute this equation, we now can be able to see that the sensitivity based on the partial differentiation with respect to g, we normally get this equation, and this equation represent the denominator of the overall transfer function. And finally, after further substitution, we can now have the sensitivity is equivalent to 1 on 1 plus g of h squared multiplied by 1 plus g of h. We now should get s tg, which will be equals to 1 over 1 plus g of h. So this now represents our sensitivity, and this can be a reciprocal of the equation such that the system will have the sensitivity of this overall gain that will increase or it will decrease based on the value of 1 plus the gain of the open loop and the feedback. Thank you for watching our video. Kindly subscribe to our channel and share this video with your friends so they can also be able to learn.